Hello, today we're going to be talking about antibody affinity and what controls it. So to get you oriented, the types of questions that we'll be able to ask once we understand antibody affinity are, how do you quantify how strong binding is between a particular antibody and its ligand? What fraction of the antibody is bound in the presence of a certain quantity of antigen? And how long does binding take to occur? So to get at all of this, we need to have a formalism for how to describe antibody affinity, and we're going to start with that here. All right, so let's consider a ligand L that is binding to a receptor that we'll call R. And so here, so the receptor is the antibody in the cases that we're talking about. These two can interact, as we know, by simply binding. So we would write that as ligand plus receptor makes a bound complex that we can call RL. And this, of course, happens at some rate, and we can write out the rate constants here with a rate of association and a rate of dissociation going backwards. And these are both little k's that we use for rate constants here. And I've written Ka and Kd for association and dissociation. So according to the laws of mass action, we can define the rate of the forward and backward reaction in terms of these rate constants. And we know that at equilibrium, these two have to happen at equal rates. So I can write that as that the rate of association has to equal the rate of dissociation. And that means that we can think about this, and this is just your sort of introductory kinetics that you would have learned long ago in general chemistry or in physical chemistry. Okay. It's worth pausing here and asking yourself, what are the units for these things that we're talking about? And so you can ask yourself, what's the unit for rate? You can pause the video and think about it. But the units for rate should be in moles per liter per second. The units for the rate constants are what it takes to give you that unit for rate. And so I encourage you to take a moment while I'm writing it and think about what it should be. So Kd should be in 1 per second, and Ka should be in liter per mole second. Okay, and so that's what it takes to get the rates in the appropriate units. All right, and so now what we can do is we can rearrange this in order to have an equilibrium constant that describes the equilibrium of the bound state or the dissociated state. And so if we want to look at the forward process, this binding, then we would have a rate constant capital K for association. That's why I'm writing a lowercase a there. And so that's equal to the rates of association over the rate of dissociation, or rate constant of those. And so then we can, of course, just write it out like this. Okay, and you can ask yourself, what must be the units of this association equilibrium constant? And that must be in liters per mole. And I encourage you to work that out if you weren't sure where that came from. Just solve out the units for each individual piece of the fraction. And then similarly, we can have a rate of dissociation, which is just going in the opposite direction. And so again, we can get it by a ratio of the rate constants or by a ratio of the concentrations. Okay, and so here the units are in mole per liter. And so you can ask yourself at this time, which of these units works better in terms of values that we would use in the laboratory? And would you rather work in units of mole per liter, which is molarity, or in liters per mole? And you can see right away why we always use Kd. It's because having your dissociation constant in units that you could actually quantify in the lab in terms of concentration is very convenient. Okay, and so it's important to note that, of course, these two are simply the inverse of each other. So KD is just 1 over the KA. And when people are talking about affinity and they say something as high affinity, what they mean is that it binds very tightly and that it's actually a low KD. So high affinity is low KD, and it's really important to have that straight from the very beginning, so that you don't get confused and think that it means actually a high KD, because that would be untrue. Okay, so at higher affinity, we get higher binding of the ligand. A higher fraction of the ligand is bound for a given concentration of the receptor, and that's a low KD. All right, so it's worth taking a moment to think about what are typical KDs for antibodies and how does this play out in the context of an immunoassay, since we've been talking a lot about those. And so antibodies, their typical KD ranges. And so if it's what is called a high affinity antibody, then usually that means KD on the order of about a nanomolar. A supposed low affinity antibody has KD on the order of a micromolar. And so this kind of gives you the bounds of what people are talking about when they say that an antibody has really good affinity. That usually means that it's on the order of a nanomolar or so. There are even antibodies that can do better than that and get down into the hundreds of picomolar range, but it can be somewhat unusual to have that. And so in terms of immunoassays, this actually plays out in terms of things that we would care about in the immunoassay, because the antibody affinity is what sets the sensitivity and the selectivity of the assay. So let me catch up. All right. And so why would that be? Pause and ask yourself. In class, I would ask you, how does the affinity of the antibody set the sensitivity of the assay? So maybe pause and ask yourself that for a moment. Okay, and so the reason is because sensitivity is your ability to detect small quantities of antigen. And by antigen here, we would be, of course, referring to the ligand. And the reason that then your affinity plays a role is because you should be able to bind up smaller quantities of antigen when you have higher affinity. Okay, so if you have higher affinity, you can bind smaller quantities, so you should have a higher sensitivity of the assay. And selectivity is a little bit different. Selectivity is your ability to distinguish between the antigen and anything else, interference. Okay, and so you can ask yourself, how would you phrase that in terms of affinity? Okay, and so the way that we do that is we're going to just look at the differences between the affinity of the antibody for the antigen and those other things. Okay, and so here we're going to be looking at that difference between affinity. And so I'll write that as a delta. It increases with delta of the KD. Okay, all right. So the last piece of this that I wanted to get to in this lesson is what controls the binding affinity. Why does a particular antibody have a particular KD for its antigen, and why might it vary for a different antigen? All right, and so we could look at this in one of two ways. One way would be to look at the biochemistry in terms of the interactions between the particular peptide side chains that are located in the antigen binding region of the antibody, and then how those are interacting with peptides or other elements that are part of the antigen. And we could look at that molecular level interaction to get at the stability of the interaction. But for today, I'd like to go back rather to something a little more fundamental, and that's actually the thermodynamics of the interaction, which of course is what those binding interactions are really getting at eventually. Okay, so binding affinity is really set by thermodynamics. And by that, I mean the difference in energy between the free state and the bound state. All right, so an increase in stability is what is needed to have binding. So you're only going to have spontaneous binding if you get an increased instability, and the only way to get an increased instability is by releasing energy. Okay, so we have to have a release in energy. All right, so for the reaction to be spontaneous, we require that the change in energy, which we're going to call the Gibbs free energy, is less than 0. And so that's what's required to have spontaneous binding. And then for that to be true, or to figure out the conditions under which that is true, we can go back to our basic definitions of delta G. So the change that we get in energy upon binding, which I'll actually write out the word binding so that we know which direction we're going with our reaction. And recall that so for binding, it's this process in the forward direction where we're getting the RL complex. And so that would be equal to then the delta G0 for that same direction of the process, plus RT ln, and then the Q for the forward direction, which in this case would be the K, the equilibrium constant for the forward direction, which is Ka. So this becomes quite powerful because now we can consider what happens at equilibrium. After everything is already bound, delta G must be 0. And you should ask yourself right now, do I really understand why that's true? And it's because at equilibrium, you've already reached the steady state concentrations for both the reactants and the products, and so there's no more change, and therefore nothing else is binding, and there's no more release of energy. So now we can set the left-hand side of this equal to 0 and then solve for delta G0 of binding, the standard Gibbs free energy for binding. And what we get is that it's equal to minus RT ln K. Oops. Okay. Okay, and that, because sometimes we want to be able to work with KDs, we can rearrange that with our properties of logs to be positive RT ln of KD. Okay, and so that becomes quite useful. It's worth reminding ourselves what are R and T, and so R is the gas constant, and it's equal to 8.3 joule per mole Kelvin. And temperature, or T, of course, is the temperature in Kelvin. All right, and so this becomes a really useful equation because it tells us that the free energy of the binding interaction, which is set by those peptide or molecular interactions that I was talking about before, is what is controlling the dissociation constant and is therefore what's controlling the affinity of your system. Okay, so let's now do a sample problem. Okay, and so here in purple you can see the problem. So let's say that you've measured the equilibrium binding constant for an antibody antigen interaction, and it's 1.3 times 10 to the 7 per molar. So I'm going to ask you to calculate how much energy is released in that process and what is the KD. So go ahead and try this, pause the video, and then come back. All right, and so I'm going to assume that you paused and tried it and came back. So the first thing to note is that what you were given was an association rate constant, a Ka, which you could tell by the units. And then you would ask yourself, all right, what equation do I use to calculate energy? And of course, that's the one that we were just given. And we're going to use the formulation where you were given it with Ka. So delta G 0 equals minus RT ln of Ka. And then we just plug everything in. And so after we do the calculation, you should get that there's a negative delta G, which is good. That means that the binding is spontaneous, of about 4 kilojoule per mole. Okay, and then the next part of the problem was to calculate Kd, which is the unit that we prefer to work in normally. And here it's just the reciprocal. So we're going to do Kd equals 1 over the Ka, and we end up with a dissociation rate constant. It says 7.4 times 10 to the minus 8 molar. Often we go ahead and we convert this to more convenient units such as nanomolar. So here it would be 74 nanomolar is our Kd, okay? It's worth taking a moment and comparing that Gibbs free energy to some other values, just so that we can know what we're talking about here in terms of energies. And so for reference, you can see if you can remember, I don't know, some of you may have learned this before, what's the energy to break a carbon-carbon bond? And so for that, the energy, it's a lot higher than what we just calculated. It's about 348 kilojoules per mole. So just, you know, 2 orders of magnitude larger than what we just calculated. That's in a carbon-carbon bond, a covalent bond. On the other hand, so this is 100-fold lower than that. On the other hand, another type of energy that we've talked about is energy from diffusion. And so the energy to move a particle by diffusion, we could actually calculate that as well. Let's say for a 1 nanometer particle, such as a protein, that's why we chose that size. And that is about 18 kilojoule per mole. And oh, I'm sorry, I just realized that I left off a 0 here, and hopefully some of you were catching that and wondering what was happening there. So here we had approximately 40 kilojoule per mole for the energy of binding, and we're comparing that, and we find that that's about 2-fold more than it would take for the protein to fuse away. So you get a bigger bonus from binding than you would from letting it diffuse away, and that's why things stay bound. But it would take a lot more energy to break up a covalent bond. Okay, the other thing that's worth noting about this relationship is that a very small change in Gibbs free energy could have a huge effect on the dissociation constant. And this matters because, for example, even just adding 1 single charged residue to the ligand might have a pretty small change in free energy, but it could have a major effect on your binding constant. All right, so that's it for this lesson, and I'd like to just preview what we're going to do in the next one is figure out how we can calculate what fraction of available binding sites are occupied given a particular KD for the antibody. All right, so in this lesson, we've learned the basic formulation for binding, how to define Ka and Kd, typical affinities for antibodies and what those affinities mean in terms of immunoassays, and then finally this thermodynamic perspective of how the energy released from binding is what really sets the affinity of a particular antibody. Okay, so I'll see you soon as we continue on with binding in the next video.